I think we are ready to start. Okay, so I'm sorry, students, I am a little bit late, and thank you very much for your understanding. As you know, let me see how many people, 72. Okay, how many people are attending? First of all, as you know, we are now in virtual mode, fully virtual mode. I just would like to make a check on the recording. Francesco, it's already recorded, or should I start the recording? Just let me know, please. It's okay.
Ok, mi dicono dalla regia che stiamo registrando.
Perfect, so we are recording. Thank you very much.
Perfetto, stiamo registrando, grazie.
Okay, thank you very much. This is then perfect. And so, as I said, we are in virtual mode. My prediction is that we will keep the virtual mode for a while. And I think, you know, I miss the physical interaction with you. On the other hand, I think that it gives maybe some more opportunities to interact with the technology and to interact through video and through direct link to web pages and so on. So let's take the advantages of this new situation. Let's take the best from the situation that we are living now. And so I'm jumping directly to the lectures, and let me open, give me 1 second that I'm sharing the screen. Let me open my website, and then let me, just 1 second. I need to share it. 1 moment. Here we are. So let's jump to our tutorials. In my website, you can have, as we said, the same links available on virtuale.unibo.it. And you see that now there are 3 lectures. I would like today to cover with you these 2 lectures, climate models and the climate change and water cycle. Now, these 2 lectures, especially the second, is a bit long, so we will see what we can cover today. I just would like to remind to all of you that next Monday you will have another teacher, Valentina Rossi, if I well remember. It's the calendar is listed here. Yes, next Monday you will have Veronica Rossi. Sorry for that. Okay, now let me open this page, climate models, and let me introduce what we are talking about today. First of all, let me make a brief 2 minutes recap of what we did, what we discussed last Monday. We discussed about the climate change problem. We basically identified the behaviors, the characteristic of this problem, and we talked about monitoring climate data. And when we dealt with climate data, we mentioned that we have different kind of information that can be used in a scientific setting to study climate change. And this information is, on the one hand, observations. And we made some examples of observations that we have available. So they are typically meteorologic weather data that have been observed for a long time span. We discussed examples like the rainfall series in Padua, the rainfall series in Bologna, and this is one kind of information. And then I mentioned that there is another information that we may use, is the information that we derive through climate models. Actually, today, much of the science related to climate change is dealt with by using climate models. So it is extremely important, even if we have an intuition of what they are, even if we have a, let's say, a preliminary understanding, because we know what they are from the mass media, from several sources. Even in this case, I think that we need to clarify what climate models are from a scientific point of view. This is the purpose of this lecture. I want to discuss with you today how are structured these models, how these models can be used to understand how future climate may behave, how these models can be used to understand the human impact on climate. Because I just would like to remind you that we identified a challenging problem from a scientific point of view dealing with climate change. The challenging problem is to separate the natural variability by the climate change, human-induced climate change. Natural variability gives risks. The climate problems that we had up to 30 years ago were all caused by natural variability. And then climate change came. So we need to be able to scientifically decipher the interaction between these two components. And climate models are a way to make a step forward in this respect. In order to deliver this lecture, I would like to open a PowerPoint presentation that I prepared. Give me 1 second. It can be downloaded at the bottom of the lecture. If you scroll down this page, you will see at the bottom of it a link. And let me jump to it. And the link is PowerPoint presentation of this lecture. So let me open this and double click on the PowerPoint, and just 1 second, I need to, okay, let me see if I can start the presentation. And sorry, 1 second, here it's let me share the screen. I need to make the sharing, 1 second. I need to share the presentation. Let me see if in this way it works. No, still not working. Or yeah, I think now you see the presentation. Just let me check. Do you see it on the full screen? Is it full screen? Okay, perfect. Thank you. Okay, so this is the presentation that I would like to use. And give me 1 second. I also need to open a web page that helps me to get organized. Okay, perfect. I am ready. So let's now move forward with the presentation, and let me start from climate predictions. So why do we use, just 1 sec, okay, why do we use climate models? Essentially, as I said, to decipher the behavior of the future climate. And essentially, we use them to get climate predictions. And these climate predictions allow us to understand how the future climate will behave. And besides understanding, we need these predictions to support the design of strategies to mitigate climate change, to adapt to climate change. And these predictions are, in climate science, are always obtained with models. We have several categories of models that we can use. And basically, what kind of models are we talking about? We are talking about mathematical models. So what is a mathematical model? You can see the definition in this slide, and I'm reading from Wikipedia. A mathematical model is a description of a system using mathematical concepts and languages. The process of developing a mathematical model is termed mathematical modeling. So the definition is quite broad, and it's a description that we make of climate, an artificial description, which makes use of mathematical relationships. And then these relationships are to be solved. How do these relationships work? Like any mathematical relationship, a model gets an input. The input is the information to feed the model. Let me give you an example. An input may be the amount of CO2 emissions. Another input is, for instance, the solar energy, because climate is governed, is fueled by solar energy. So you have to give a prediction of the solar activity in the future in order to run the model. This input is digested by the model, whatever form it has. It can be like in this figure you see in the PowerPoint. It may be an empirical model. Black box stands for empirical. It may be, and this is the case for the most recent climate models, it may be a model that is so-called physically based. What does physically based mean? It means that we try with mathematical relationship to translate into the mathematical domain what we observe and understand of the real world. When we say that a mathematical model is physically based, it means that we try to translate the real world that we observe into a mathematical frame. And this is very useful because if you have a means to simulate, to reproduce what happens in nature, you can test alternative hypotheses, like, for instance, what if the CO2 emissions don't decrease? They keep increasing. What if in this case? And then the model produces an output. The output from climate models is diverse. Generally, the most sophisticated models include in their output a lot of weather variables, temperature, rainfall, wind speed, etc. So physically based models are not the only one option. We can also use statistical methods. And statistical methods have a different approach. They don't try to make an interpretation of the physics, but they try to use the observed climate in the past to extend, to make a prediction, to extend in the future what we observed. Is a different approach. And of course, the statistical model, one main weakness is that it may not take into account what is changing now. If you take the past and reproduce the past into the future, you may not take into account relevant changes that are occurring now. On the other hand, if you reproduce the statistics of the past, you take into account the knowledge that we derive from what we already observed. You can already understand that the physically based model and the statistical models are different. They have pros and cons. They have limitations and advantages. I can anticipate that probably the best way forward to improve our predictions of future climate is blending the two approaches. Okay, so we need a mathematical model, and let me make a brief historical remark. So when did we start? When did humans started to build mathematical models sorry, I went back and forth, mathematical models of climate. So we basically started with the development of conceptual and very simple models already in the far past. For instance, we know that the Greeks understood that the shape of the Earth is spherical and connected climate change with the changes in the inclination of the terrestrial axis. And so this is the very early, these are the very early developments. And it was in the 19th century that more sophisticated models of energy balance and radiative transfer came. And it was in the 19th century that the greenhouse gas was first understood and first postulated. Let's say that computer simulation models of the atmosphere were first introduced around 1950, because it was around that time that computers became for the first time available to produce complex simulations. Mathematics before than that was done by hands. So you understand the big, it was a giant leap forward, the introduction of the computers. And from 1990, with the increasing awareness of the climate problems and the increasing availability of computers, that these kind of models, mathematical models of the climate system, developed a lot, and they are still developing. Now, in order to understand how a model is structured, we need to understand how climate works, the basics. We need to understand, as we said, the science behind it. Let me start with a description of the atmosphere, because of course, the physical entity that we are trying to reproduce is the atmosphere, which is connected with other physical entities that are located over the Earth. So they are like oceans, like, for instance, lands. Of course, they play a role in governing the climate by interacting with the atmosphere. But now let me focus on the atmosphere. You see here a sketch of the different layers in this figure here. You see a sketch of the different layers of the atmosphere, from the troposphere, which is the part that is closer to the Earth's surface. And then we have the stratosphere, the mesosphere, the thermosphere, and the exosphere. And it's not necessary that you learn the denomination of these different layers. I think it is instead important that you try to fix in your mind the 5 main subdomains in the whole climate system. These subdomains are the atmosphere, we already discussed it, with its several layers. And then we have the cryosphere, the hydrosphere, the biosphere, and the technosphere. Okay, let's spend a few words on each of them. So the atmosphere, it's the layer of gases, commonly known as air, retained by the gravity force and surrounding our planets, is composed by 5 main layers. You will see also another figure in my webpage. Now let's talk about the cryosphere. The cryosphere is the domain of water in solid form, which includes sea ice, lake ice, river ice, snow cover, glaciers, ice caps, ice sheets, and frozen ground, which includes permafrost. There is a wide overlap between the cryosphere and the hydrosphere. The cryosphere plays an important role in the Earth's climate. In fact, when you listen to the media, they are much concerned by the melting of the ice caps, because this is a driver for sea level rise. It's a driver for, it provides feedbacks on the climate system that have an influence on the radiation, on the solar reflectivity, etc. So it's indeed, it plays a dominant role. What is the hydrosphere? The hydrosphere includes the mass of water found on the Earth. When I say on, I mean over the land, under the land, and in the planet's crust, let's say. Water in the liquid state covers about 70% of the Earth's surface. We know this from the primary school. Oceans cover 70% of the Earth's surface, and about 97% of the liquid water is found into the oceans, which means that 97% of the total water over the Earth is salt water. Okay, biosphere. It's also known with the term ecosphere. It encompasses all the ecosystems, and it can be also called the life zone of the Earth. The biosphere it's interacting, of course, with the hydrosphere, because as we know, water is strictly related to life. And then we have the so-called technosphere, sometimes also referred as anthroposphere, is the part of the environment that is made or modified by humans for use in human activities and human habitats. It is a term that was first introduced in the 19th century by the Austrian geologist Eduard Suess. He was, he was a great scientist. If you don't know about Eduard Suess, I suggest that you have a look at his biography in the web, because I think he would deserve more popularity than what he has now. He was really introducing new concepts, and he introduced this terminology, which paved the way to the introduction 100 years later of the term Anthropocene by the Nobel Prize winner Paul Crutzen, who, by the way, is just passed away. Paul Crutzen passed away 1 month ago. Now, the technosphere is continuously developing and has reached a level of interaction with the climate systems that humans never experienced before. We know that. So this kind of interaction probably is also inducing changes in climate, not probably, for sure, we said. These subdomains are, sorry, I go back one slide. These subdomains are open systems. What does it mean, open systems? It means that energy and matters like water, for instance, can move in and out from these domains, can move to one domain to the next. Let's, for instance, think about water. Water is an essential element of the climate system. Water can move from the hydrosphere to the atmosphere through evaporation, and can go back in the form of rainfall from the atmosphere to the technosphere, biosphere, and again, oceans. So these are open systems. The fact that they are open means that they are connected. So if we cannot describe one of these systems alone, if we want to describe climate, we have to describe with mathematical relationship these systems and their connections. You understand the complexity, because there are some connections that we still don't understand. Let's make it clear. Sometimes we get the feeling that we know everything of what is related to climate. We know everything that is related to nature. But this is not the case. And this is one first thing that we have to fully digest. There are things in nature that we don't know. Look at the pandemics. The pandemics is a clear example that there are some processes, some organisms in nature that we still don't understand. And so translating into a mathematical model something that is not fully understood, it is on the one hand, it's complex. On the other hand, it's fascinating. Okay, now let me talk about the biosphere, because this is something that it's very close to my heart, and I think it is very interesting. So let me describe the distribution of water storage over the Earth. I'm talking about storage, not fluxes. So if I take a picture of water over the Earth at a given time, what I can see is that, as I already said, look at the column on the left, 97% of water is salt water in the oceans. And then we have one more 1%, which is other salt waters besides the oceans, like salted lakes, etc. And then we have fresh water, 2.5%. This is the part of water that we can use. If you explode this 2.5%, it's exploded in the middle column. And you see that of this 2.5%, the great majority is water in the glaciers and ice caps, almost 70%. And then we have groundwater, and then we have 30%. And then we have surface water, 1.2%. Let's explode it. Part of it in the right column, it is exploded. This 1.2%, which is 1.2% of the 2.5% in the left column. This 1.2% is exploded in the right column. And you can see that ground ice and permafrost includes most of it. And then there are lakes, living things, river, atmosphere, and the soil moisture. So you understand from here that this huge amount of water that plays a relevant role into climate, the part that can be used by humans is basically, it's 30% of 2%, which means 1% of the total amount of water is one drop into the ocean, which is interesting, I think. And now let's focus on let's focus on these systems, which we already mentioned, to give you a more detailed description of how we can translate into a mathematical model their interactions. So, first of all, what is the driver of the climate system? It's solar energy, as we already said. And Earth is heated by sun in an uneven way. Some part of the Earth receive more energy, therefore originating differences in temperature that the system, the Earth system, tends to reduce by transporting heat from the tropics to the ice zones of the poles. And this heat transportation gives rise to ocean currents, wind, evaporation, precipitation, and global weather pattern. Some of the solar energy is reflected back into the space, while the rest is absorbed and by the climate system and re-emitted as heat. And this heat dynamics is what reflects the temperature of the Earth. So I already mentioned what is written in the first row of this slide, the uneven distribution of heat. And let's say that the ocean atmosphere system, this is important to emphasize, also exchanges gases like carbon dioxide, where the ocean acts as a huge carbon sink. There is a lot of CO2 that is stored into the ocean. And if you heat the climate system, and therefore we cause the ocean heating up, what happens is that the oceans release CO2. So this is a positive feedback, meaning that if for some anthropogenic reason you increase the temperature of the Earth by increasing CO2 emissions, for instance, then the ocean may react by releasing more CO2, therefore causing a further increase of the greenhouse effect. And this, of course, is something that may accelerate global warming. This is something that may bring an initial perturbation to an irreversible state, because, of course, in order to store more CO2 in the ocean, we would need to cool the ocean, to decrease the temperature of the ocean. But this is, of course, not possible if the temperature of the atmosphere is increasing. So all of these interactions must be deciphered into a model. And let me now discuss with this slide an important behavior of the climate system. the climate system may be chaotic. What does it mean, chaotic? I'm sure that you know the paradigm of the butterfly that flies in Japan, and it is alleged to be able to trigger a hurricane, a tornado in the United States. What does this mean, that paradigm? It means that if you have a small perturbation of a chaotic system, this small perturbation may evolve into a huge perturbation somewhere else. This means chaos, means that small perturbation can develop, feed themselves, increase and increase to a state where the perturbation is not negligible anymore. And the presence of chaos implies that the system, it is often said, it's non-linear. And non-linear means that the system is, we don't really need to understand what non-linearity is in mathematical terms. Let me say that non-linearity means that the system can react in a very strong manner to a small perturbation. And non-linearity also means the presence of tipping points, which we already discussed, at a stage in a system where a small perturbation may bring the system to a completely different state. The presence of chaos is important, first, because the climate system is clearly chaotic, but it has also another very important implication. The important implication is that it's difficult to predict the future evolution of a chaotic system. This is another issue that we have to take into consideration, because our objective with the climate model is to predict the future. And basically the presence of chaos, which is recognized by the scientific literature, there is no doubt on that. The presence of chaos means that the system is difficult to predict. Let's say that a chaotic system can be predicted in the short term, but in the long term, it becomes unpredictable. You may ask the question, what do you mean with short term? It depends. It varies. The predictability of a chaotic system, it's varying depending on the chaotic behavior of the system itself. And this time of predictability horizon, time horizon in which we can predict a climate system is called the Lyapunov time. Again, we don't need to remember what is the Lyapunov time, but if you want to understand the science of climate, you have to get what a chaotic system is. So my suggestion for you is try to get information on this, because it is essential to understand predictability of climate. I still have 5 minutes to go before the break, and let me now talk about the structure of these models. And again, what is the purpose of the models? So let me summarize, because I said we have two main purposes. Understanding, because when you build a model, you can check, you make assumptions. You are describing a system that is partially unknown, which means that there are some things that you have to assume. Like, I don't know if the wall in front of me is black or white. So I assume that is white, which means that I can build a model of the reflectivity of the wall. And if the wall is white, it will, my model will take into account the performances of a white surface to reflect, for instance, light or heat. And then I can compare the model with what I observe. If I see that the model gives a reflectivity that is higher of what I observe, it means that the wall is not white. It is probably black. At the same time, with the climate system, in the same way, you can test hypotheses. So let's suppose how the climate system works for the processes which I don't fully know. So let me assume that the climate system reacts to greenhouse gases concentration in a certain way. And then I apply the model. And then I check the model with what I observe. And this is a way for understanding. A second purpose of the model is reproducing the future climate. And let me say that very often we assume that these two purposes can be achieved with the same model. Actually, it's not like that. I mean, if the purpose is to support engineering design, I need a different model with respect to the situation where my purpose is understanding. Okay, and let me say that the models can range from very complicated solutions to simpler ones. And for instance, the most complicated solutions are the so-called global circulation models. They try to reproduce the whole climate system. They are called the GCM models, GCM, global circulation models. But there are also simpler models. Now, I think, okay, let me also move forward with this slide, and then I'll take some time to for the break. So these GCM equations describe the evolution in space and time of relevant atmospheric processes. Keep in mind, evolution in space and time. It is a complicated process. And these processes are rapidly changing in space. So we say that they are heterogeneous, and rapidly changing in time. So we say that they are non-stationary. And therefore, in order to describe this variability, the model needs to split the Earth's surface and the Earth's interior in small subdomains. Look at the figure. You see a grid. The Earth's surface, the atmosphere, is split into a grid. Why this? Because in order to describe this high variability, the model equations need to be applied at the local level. You cannot use the same equation all over the world. If you use the same equation all over the world, you don't describe the internal variability. If we want to describe the internal variability, the variability in space and variability in time, equations should be applied at the local level and at each individual time step. Which means that then each application in space refers to a small rectangle or a small square, and you have to describe the interaction of each grid with the neighboring grids. So the mathematical model is applying tons of equations, and in order to get what is called a 3D representation. Okay, now let me now take the break for 15 minutes and then I'll move forward. Do you have any questions so far?
Yes, there is a question on the chat by Mattia, who said, is this also called a Ciclidi feedback? I don't know what he was referring to. You need to turn on your microphone, otherwise we, yeah.
I'm sorry. So Ciclidi feedback means feedback cycles. And it means that you have a kind of a series of feedbacks that are related to each other. So for instance, let me give you an example. You may have increase of temperature in the ocean, which causes an increase of evaporation. And then the atmosphere gives a feedback. The feedback is formation of clouds and subsequent decrease of temperature. Because once you have clouds forming after evaporation, you are putting a screen against the solar radiation. And then at the same time, the clouds originate rainfall. Rainfall compensate evaporation. So it gives a return feedback. And it also gives a return feedback in terms of temperature, because rainfall is lowering the temperature of the Earth. So basically, you get feedback of the increase of temperature by the atmosphere. And in this case, the feedback gives a compensation. And so this is one, it's an interaction that goes back and forth, okay? And this is called cycle. And in this case, given that the feedback, the example that I made is compensating, then the cycle is in a way interrupted. But it may happen that you have a feedback that is originating a cycle. And let me make another example. Increase of temperature in the ocean, CO2 emissions from the ocean. I already made this example before, which means that you have an increase of the greenhouse gases concentration, and then you have a feedback that causes an increase of air temperature, which gives another feedback, which is increase of the ocean temperature. And then another feedback from the ocean to the atmosphere, increase of CO2 emission. In this case, you see the cycle. And the cycle is causing an iteration, which brings temperature up and up. This is the cycle of feedback. I'm not sure if, when you asked the question, if you referred to feedbacks between grid cells. In this case, we don't call them feedback. In this case, we call them fluxes, fluxes of matter and quantities, like fluxes of energy. In this case, is a flux of a quantity, or you may have a flux of water from each grid cell. This is a flux of matter. And in this case, we call them, again, fluxes, not feedbacks. I hope I answered the question. Okay, so let's let's take 15 minutes break. Thank you. Like, let me think if I can make an example. Yes, a very trivial example. Let's suppose that you don't understand how it works tossing a coin. And then you know, it's a process. It's a physical process. Tossing a coin is a physical process. And how can we try to make a prediction of this process? There are two ways. The first is what we may call an empirical approach, which actually is statistical. So you make an experiment, you toss the coin several times, and you realize that half of the trials you get an head, and half of the trials you get a tail. In order to get this information, you need to try several times. You cannot just try once or twice. You need to try a lot of times before being able to say that it's 50% the chance that you have getting an head. Indeed, a famous statistician, Carl Pearson, tossed the coin 24,000 times, and he got head 12,000 plus 12. So he concluded that this is, this was his prediction. I have 50% probability of getting an head. This is an example of a statistical model. Statistics is based on experiments. Now, on the other hand, you may devise a different approach. You may say everything is known about tossing a coin. You put the coin on his toe, on his thumb, on your fingers, and then you toss the coin by giving a certain force to the coin itself, and you give a direction which you may use as input data to your model, and then you predict how the movement of the coin will evolve. Everything is known from a physical point of view. This is possible to do. Indeed, some people tried to. And this is an example of a model where from the initial conditions, like the position of your hand, and from the input data, the force that you give to the coin with your fingers, etc., you can build a mathematical description through physics of tossing the coin. You understand that this kind of approach has limitations. Why? Not because of the lack of knowledge. We know everything of the physics behind tossing a coin. The limitation is that a small change in the input data, a small change in the position of your finger completely changes the final outcome, which means that the process is chaotic. There is a strong dependence on the initial conditions of the process you are studying. So this is a perfect example of a physically based model that would be well formulated, but still it's not predictable. The process is not predictable on an individual basis because of chaos. So I think this gives to you an example of the statistical model that tries to make experiments, and the physically based model that tries to explain with the physics. Now, there might be an alternative approach, which is you make a statistical experiment, and after a while, you realize with intuition that it's indeed clear that when you toss a coin, you have equal chances of getting an head or a tail, which means that you can give 50% to one and the other. But still, you may need to make some attempts to get a confirmation of this. This would be an example of a statistical model that is supported by physical interpretation, which is a blended model. So you don't really realize a physically based model because you get to the final outcome with your intuition, but still your intuition is using physics. So this is a blended model. I hope now the difference is clear. And for climate, it is the same thing. You may understand climate by looking at your observations in the past. And this would be great if we had long observation periods, if we had observation of climates that go back 2000 years. This would be great. We wouldn't need a climate model. The observations would be fine enough in order to understand. Unfortunately, we don't have the observations, so we try to build the climate models by using what? Process understanding and the law of physics. Is this clearer now, or do you think I need to give more explanation on this? And okay, I move forward, but okay, thank you very much, Giacomo. I move forward, but please step in with questions if you have any doubt. And once that I share the screen, I also ask for your help in letting me know. I try in any way to visualize the chat independently. Okay, now let me share the screen once again. And I think, let me try with this one. Okay. Okay, very good. Now let me bring this. Very good. So we were talking about grids. Okay, this is fine. Now, how many squares do we have? How many grid cells we have? With increasing model complexity, the resolution of the models is increased as well. So now we have models working at a quite fine spatial scale, which means that the size of the grid is about 5 by 5 kilometers. This means that you need millions of grid cells to describe the system. And, you know, this means that the computational requirement is very huge. Okay, and keep in mind that even the 5 by 5 kilometers spatial scale is still not enough detailed for our purposes in many cases, and therefore we need to you know, adopt finer spatial resolutions. Okay, let's move forward with the next one. So what are the candidates equations to describe the system? Now we talked about the laws of physics up to now. I want to be more detailed by saying that we are essentially using conservation laws. The conservation laws state that a specific measurable property of an isolated physical system does not change as the system evolves over time. Let me give you an example. The total amount of water mass in the climate system is conserved. There is no losses in terms of water. Water may change its state from liquid to ice to vapor. It may change its position. It may change its distribution in time, but the total amount of water in the Earth system, in the climate system, is conserved. And this is a classical example of a conservation law. It is precisely a mass conservation law. What are the physical quantities that may be conserved? For instance, energy. Mass, I already said that, or water vapor. Let's forget about momentum. Those of you that have a background in engineering or in mathematics know what momentum is. It's related to energy. It's a vector rather than a scalar, but I don't think we need to go into these details. Let's focus on energy and mass of, for instance, water. The models are based on these equations. Conservation of energy allows us to describe the movement, for instance, of water in its different states: fluid, liquid, ice. Now, so what are we describing? We describe through a climate models how energy and materials propagate through the climate system. The climate system, which includes the atmosphere, land, and oceans. And, you know, it's running this models, as I said, requires a lot of computational effort. And these facilities, the facilities that we need to run climate models, are only available at a limited number of computational centers around the world. So this is why we have a limited set of climate models. These climate models, as I said, rely on assumptions, something that we don't understand, and we have to assume for true, which means that we assume, for instance, that with increasing temperature there is increasing evaporation, which is not actually true, because still it is debated if an increasing temperature gives more evaporation. But we assume that. This is an assumption. And of course, if you make different assumptions, you obtain different models. And in fact, we don't have only one model of the climate system. You may think that once a system is known, there is only one model for describing it. But our system is not fully known, and therefore different assumptions lead to different models. And it's an exciting exercise to compare them. And these assumptions become less and less heavy as we improve our knowledge, but still there are a lot of them. And therefore, it becomes important to compare models, and to compare models with the observations. But I will talk about this later. So what are the input and output from the models? Let me give you more details. I already gave some examples, but I want to be more specific. The input data are the driving forces for the climate itself. Solar forcing, I already mentioned it. And there are other input, and a relevant one, which is also related to the human impact, is the concentration of greenhouse gases like CO2, methane, and etc., and others, as well as aerosols. Beware that while the effect of greenhouse gases like CO2 and methane is already known with good detail, the effect of aerosols, it's still something that we are learning. And aerosols really influence cloud formation because their particles act as a catalyzer for the condensation of water in the atmosphere. But the dynamics, the modalities of these processes are not fully known. Okay, and let me talk about the emissions, because this allows me to introduce a critical aspect of climate models. The CO2 emissions, we need to anticipate what they will look like into the future up to 2100. And so basically what we do is to make a prediction of the emissions. We make a prediction of the CO2 emissions for the coming decades. We make a prediction of the model inputs. And these predictions are based on different emission scenarios. I think I will describe later what in detail what these scenarios are. For now, let's take that we have several scenarios of future CO2 emissions, which depends on future policies for mitigating them. And output data are a lot of information. And it is important that here we make consideration. So the models, for instance, allow us to predict temperature. The models allow us to predict rainfall. But not all the variables are predicted with the same precision. Actually, when we compare the output from climate models with what we already observed, because we can do that, we can run climate model in a hindcast modality, which means that we simulate what we already observed. When we do this, this comparison should tell us whether a model is reliable or not. Actually, for some of the variables, this comparison gives satisfactory performances. For other variables, this comparison tells us that the model is still very uncertain. So it is quite accepted that the models give good performances in the prediction of temperature, for the component of the hydrological cycle, for rainfall, for wind speed, for snowfall. Still, the reliability of the performances is very limited. It depends on the scale of representation, meaning that if you compute average rainfall over a large portion of the Earth, like a continent, then you get, and maybe that you also average in time, like annual rainfall over a continent, maybe that you get good performances. But if we go at the local level and the local time, then there is a lot of uncertainty. And the problem is that models that may be good in predicting rainfall over the United States, then when you move to Europe, they are not as good. The performances depend on the location. So this is to mean that there is uncertainty, and in some of the variables, the uncertainty is really huge. And this is something that it's not clear if you look at the media, if you look at the public information. And it's clear if you look at the science, if you look at the research, if you really look at the details of the papers, you understand what the uncertainties are. And then you understand that if you look at the driver of the hydrological cycle, which is also the driver for floods, for droughts, and if you look at small scales, I mean small spatial scales, small temporal scale, then there is a lot of uncertainty. Just 1 second, I want to give a look at the chat because I want to make sure that I'm not losing anything. Okay, here it is, perfect. No questions. This is something really relevant, especially if you are involved in the design of structures. So you have to be fully aware of what are the variables that are well predicted by the models and what are the variables that are more uncertain. And let me now focus specifically on the time step. What is the time step the models are working on? We already talked about the spatial scale. I said 5 by 5 kilometers. In terms of time, typically the time step is about 30 minutes. But very often the output is given in the form of an average over longer periods, precisely to minimize uncertainty. Okay. Let me give you an example of a climate model, a very simple example. Now I want to give you some examples, and then I will talk about uncertainty again. Now, this is an example where what the equation that you see here is an example of a very simple model that is applied to the whole Earth system. So there are no grids here, which means that I give a unique variable for the whole system. And what is the variable which I want to predict here? And the variable is temperature. It's T, okay? And it's the T in the relationship is temperature. And I see that there is, in the list of the variables, I forgot temperature, so I have to amend it. And here, if you look at this equation, it is just a very simple relationship where S is the solar constant, the incoming solar radiation per unit area, which is about 1300 watt per square meter. And then A is Earth's average albedo, which is about 0.3. We don't need to go into the details of what albedo is. Let's say that it's just an essential physical behavior of the Earth system. R is the radius of Earth, which is about the value that you see on the slide, and which is well known. Sigma is the Stefan-Boltzmann constant. It's a constant. It's a specific behavior of the Earth system. You see the value here in the slide. And epsilon is effective emissivity. Okay. If one solves this equation for temperature, one gets this solution. Please note, you don't need to learn these relationships by memory. I go back to the previous slide. These two relationships are provided here to give you an example. So don't worry if you don't understand the physics behind it, because this is a physical model. It's not a statistical one. You understand? I want to give you the example of what a physical model looks like. So you see physical quantities that are included here, and this is essentially a conservation law for heat. Okay, so these equations and the resolution that you see here, again, it's not necessary that you learn by memory. It's interesting that you notice that from this very simple model, if you solve for temperature according to the relationship that you see now on the screen, basically you get an average Earth temperature of 15 degrees centigrade, which is correct, which means that if you average over the whole Earth and you average a long time, because this is something where anything is assumed not to change in time. Solar radiation, the other quantities, they are assumed to be fixed in time. So if you average over the whole Earth and you get everything frozen in time, you get a good and reliable response. And also, this gives to you an example where a comparison with what we observe tells us that the model is correct. So I think it is really a very good example of a very simple model. And of course, when you go to GCM, you include a lot of other variables. It's not only temperature, it's rainfall, and you include the fine spatial and temporal scale. So it becomes more complex and uncertainty increases. And there is in my web pages a nice video which explains how different climate models work. And I think it is a video which is very, I mean, it's for dissemination. It's easy to understand. I suggest you to have a look. It's very short. Now, let me talk again of the emission scenarios, because this is something that it's strictly related to uncertainty. Now, I want to make a focus on the reliability of these models. We understood how these models works, and we just focused for now only on the physically based models, on the GCMs. We said they are based on reproducing the physics through mathematical relationships. They are applied at the local scale, and they need input data and they deliver output data. And we mentioned emissions. Now, how emissions are identified? First, beware that in 2013, climate scientists defined a new set of emission scenarios, which are called representative concentration pathways. To predict the future scenarios of CO2 emissions I mean, it's an impossible target in principle, because you need to make prediction of the social evolution of society, on the socioeconomic evolution. And of course, this is another chaotic system. The human system, society, is highly chaotic. If you make a small perturbation, you may end up with completely different results. And let me make the example again of the pandemics. The pandemics brought our global emissions to reduce about 30%, which is a target that is perfect, is spectacular, but nobody could predict it. We couldn't predict that it would be a global emergency, reducing our emissions. And, you know, so you really understand that the prediction of the future scenario is I mean, it's really complicated. These are the scenarios. Again, you don't need to focus to learn by memory them. And let me just show you this article, and which it's displayed here. And let me see if I can get the related web page on the screen for you. I hope that you can see everything. Yes. Okay, let me have a look. There is a picture in this article. It was published on Nature, and it's not really a scientific article. This is a comment. I want to show you a picture of the emission scenarios because I think this picture is perfect to explain what I mean. So these are the various scenarios from 2013 to 2100. First, I want to tell you a curiosity. I think this is a nice figure. So I wrote to Nature. I explained that I wanted to show it to students, and I wanted to include it in my tutorials. And I asked for permission. And they said that I could use it for teaching, but I had to pay 62 euros of royalties. So I decided that it's much better if I show you the picture directly on the link. And this requires you to click on the link. But given that this is an open access paper, I really don't understand why one should pay for including a figure in an open access paper in a tutorial for students. But anyway, we know that we are moving towards open access scientific publishing, and I hope that this comes soon, because I think for education there should be no barriers. Anyway, these are the various scenarios, and you see here the acronyms: 0.5, 7.0, 6.0, 4.5, 1.9, and this means and here you see that on the vertical axis you have the global fossil fuel emissions. So from this figure you understand that the worst case, no policy, it's also called business as usual, is termed with the acronym 0.5, RCP 0.5, and representative concentration pathway RCP 0.5. This is considered to be highly unlikely. Okay, but still many of the predictions of climate models are done by referring to this scenario. And then there are the other scenarios, and the likely ones are those from 4 to 6. And they basically predict a decrease of the emissions. Of course, there is a lot of discussion. You have to be aware that when you get a prediction of a climate models, you have to get information on the RCP that has been used. Now, let me go back to the presentation. And here are the scenario, and you can recognize the numbers RCP from 1.9 to 8.5. Again, it is considered unlikely 0.5, and it is frequently discussed, the opportunity to use this scenario for predictions, because actually it is really unlikely. Now, uncertainty. Uncertainty assessment is a core topic for all the disciplines involved in environmental modeling. And let me say, oh, I'm sorry, there is a question in the chat. It's smaller interval means more uncertainty. What do you mean? Smaller intervals in what? Not in the emissions, I think. Let me see. The question is 10 minutes old. So let me see. What do you mean by smaller intervals of what? Can you please write on the chat or step in with the micro? Smaller interval. Okay. Yeah. Okay. Yes. Very good question. Yes. Smaller intervals means a finer description. So a more detailed description. But the more detailed description introduces more uncertainty. And it's, you know, I think I should give you an example of something. Let's suppose that you want to describe the temperature in your house, and you have a first model that describes the average temperature. And let's suppose that now you want to build a finer model that describes the temperature in each room. So you may think, oh, this is a more refined model, so it's more precise. Actually, the model is more detailed, but it's not necessarily more precise, because in order to describe the temperature in each room, you need to know, for instance, the surface of the windows and the kind of windows that you have, the kind of glass in the windows. So it means that the detailed model requires more information. If this information is given with uncertainty, you increase the uncertainty of the model. So for instance, if you want to describe the temperature in the whole house, you don't need to describe the windows in each room. You can just put an average description of the windows. And this average description is likely to be more representative because it's an information that it's more easily taken. In terms of climate models, if you need to describe the solar emission in each grid cell, this is what we need to do, you understand that you need a survey, an estimate of solar emission that it's much more detailed. And in this case, if you don't have this description, because you don't have a satellite image describing at that resolution, you introduce more uncertainty. And in general, keep in mind that the more the model is complex, this applies to any environmental model, the more the complexity, the more the information that you need to fit the model, and the more the uncertainty. So it's a balance that you have to make. So can I apply a complex model for describing something? My question for you would be, do you have the detailed information? If you have the detailed information with small uncertainty, go with it. If you don't have the detailed information, just forget about it because you are increasing uncertainty. I hope it's clear. Okay, and now, as I said, uncertainty assessment is a topical issue. And what are the kind of uncertainty that we are facing in climate modeling? Before I start, let me say that in environmental modeling, uncertainty assessment is a classical topic. In different disciplines, we use different methods because it depends on the available information again. So we are concerned about, in climate modeling, forcing uncertainty, model uncertainty. What is model uncertainty? Forcing uncertainty is the kind of uncertainty I mentioned before. It's related to the fact that we observe data that we need to use into the models, and these numbers, these data are uncertain. Okay, what is model uncertainty? Model uncertainty is due to lack of knowledge. So we make these assumptions that I mentioned before, which means that even if I used perfect input data, even if everything is perfect, the model still would be uncertain. The output would not be the same as what I observed. Why? Because there are processes that I don't know, and therefore I can't reproduce them with a full precision. And then there is the uncertainty over the initial conditions. Any of these models need the initial condition. When you toss a coin, you need to know the initial positioning of the coin. When you simulate climate, you need to know from where you are starting from. The initial temperature, the initial position of the butterfly who flies in Japan and may create a tornado in the United States. And it may happen that if the butterfly is in a certain position, nothing happens. If the butterfly moves just 1 meter, then you get the tornado in the United States because the system is chaotic. And these are the 3 types of uncertainty we are concerned with. So basically, how climate modelers try to estimate uncertainty? By recognizing these 3 sources of uncertainty, they decided to run several models. if forcing is uncertain, why not to run the model with several different plausible forcing? If the model is uncertain, why not to run several different models? If the initial conditions are uncertain, why not to run the model with several different initial conditions? And then you end up with a lot of simulations and you get an envelope, a range for the predicted variable. And then they say the truth is within the range. Let me see if I have a picture to show you. And I think I already discussed about these slides, but let me jump to the picture, next one. And you see that there is a green line, which is observations. What is reproduced here? The mean temperature. It's anomaly of temperature. What is anomaly? It's the difference between the long-term average. So when you see minus 0.2 at the beginning, minus 0.4, it means that at the beginning, the temperature was lower than the overall average by 0.2, 0.4 degrees centigrade. When you read plus 0.4 at the end, it means that we are above the average. And this is quite normal because you know that from 1900 to 2000, we got an increase of temperature. Now, observations are the green line. And you see the simulation given by two different models, the Canadian model and the Hadley Center model. These are very well-known models. And you see that their response is different. So you can identify a range. You see that the Canadian model is better at the beginning of the period, maybe, and it ends up with an overestimation of the warming. You see that the Hadley model is not much precise in between 1940 and 1980, but at the end of the story, it seems more reliable at the end of the period. So if you encompass different models, if you encompass different initial conditions, different forcings, then you get a plausible range. I think I have another figure. Let me jump forward and then I get back to these slides. Another figure is here. These are the global warming projections up to 2100 given by different models. And you see that indeed we get a range, and the range is quite large. We go from an increase of temperature that with respect to the long-term average that is ranging from +2 to +5. So in this range, we can say, we are allowed to say that probably there will be the truth. But you know, this is just an example, and then we should run other models with different initial conditions, and we may get different responses. And then we may compute, for instance, the average in order to get the best prediction. This is the way uncertainty is estimated. Now, let me jump back to and then 5 minutes, and then I make the second break. Let me jump back to the previous slides. And okay, so, oops, sorry. Okay, and I think this was already discussed. Yeah. Now, what to say about this technique for estimating uncertainty, which is called Ensembl Prediction. And these ensemble predictions give a range of the prediction itself. This range is expected to encompass two sources of uncertainty that were described before. The first is the error introduced by the use of imperfect input data and initial conditions, because we run the models to produce the ensemble with several possible input data and initial conditions. So we encompass this uncertainty. And then they are assumed also to reproduce the errors related to model structural uncertainty. So you get something that you may think it solves the problem. Now, let me make a consideration which is extremely important. In other fields of environmental sciences, like for instance, I am an hydrological modeler, so I know how we estimate uncertainty in hydrological models. We realized and we proved that there are scientific contributions that have nothing to do with climate change. We realized that ensemble predictions with different models very often provides a false estimate, a misleading estimate of model structural uncertainty. Because you can easily understand if you have a set of models that are all wrong, you get a range that may not encompass the true prediction. Because, of course, if you try to estimate uncertainty in this way and you don't have the correct model available, all the models are wrong. And therefore, you are not granted for sure that the true prediction is in the range. So this kind of ensemble prediction is very useful to provide a scenario, an estimate of uncertainty that reflects the assumptions that you made. But if these assumptions are all wrong, this is not providing an estimate of the true uncertainty. The true uncertainty means that we have a range that with an assigned probability may contain the true value. This is the rigorous definition of uncertainty. It's not necessary that we understand what it means. What I want to say is that one thing is estimate uncertainty regarding a given assumption. Another thing is to estimate uncertainty for the purpose of design, where I have an obligation by law, the responsible professional, typically the engineer, has an obligation, as a legal obligation, to take uncertainty into account in a way that is suited to technical design. So it is extremely important to say, and this is something that you don't find in any guideline, in any technical guideline, and you may find only in very few publications in engineering journals. It's very important that you take into account that the ensemble uncertainty is not a good estimate for the sake of design. It is useful, again, for the sake of checking assumptions, but not for estimating what I call the true uncertainty that I need for technical design. So it is extremely important that we separate the two things. One thing is scientific uncertainty. One other thing is uncertainty for technical purposes. They are related, but are not the same thing. And this is a message that I wanted to convey to you. I think we can now make another 15 minutes break, but I wonder whether you have any question. Okay, please feel free to write on the chat meanwhile. I take a break myself, but if you want, just be aware that after the break, I will start by looking at the chat and answering questions. Thank you very much. So in the chat, I don't see any question. So I think I can move forward by sharing the screen. One second. Okay, we are not yet at the conclusions. Okay, now let me just get the chat in the second screen. Okay. Okay, very good. Now, this figure that you see on the screen, again, it's what I have shown before. So showing these ensemble predictions for the specific case of temperature. I just want to emphasize once again that one thing is uncertainty in the simulation of temperature. One other thing is rainfall and other variables that are more highly varying, because temperature is more heterogeneous, is slowly varying in time. When we talk about rainfall, we talk about a process that is more chaotic with respect to the process governing temperature, and therefore beware that uncertainty can even be more relevant. So what is the moral of the story so far? The moral of the story is that we currently use these GCMs, and they are continuously evolving. So keep in mind that things can improve in a relatively short time span. If you go back 3 years, for instance, in 2017-18, the models were different. If you go back 10 years, they were tremendously I would say much less evolved. So probably the field will evolve even more in the near future. And again, the moral of the story is that at our current stage of knowledge, we may conclude by saying that these models are very good for testing hypotheses, are not really very satisfactory for supporting the design for the identification of actions. So what could an alternative be? I already mentioned statistical models. So let's spend only one slide on what's the articulation, the main difference of statistical models with respect to physically based one. So what's the difference between the GCMs and statistical models that could be used? In order to, let me show to you the next slide. The next slide talks about stochastic simulation. What is stochastic? Stochastic, you can take this word as a synonym of statistical. Actually, this is not a really rigorous definition, because stochastic is actually a synonym of random, I would say, which means that it's a model that is trying to get uncertainty into account. In uncertainty that comes from our limited knowledge of the system, comes from our limited capability to observe the input variables. So again, take, for the purpose of understanding what I mean, take stochastic as a synonym of a statistical model. And it is this kind of approach, stochastic simulation, statistical simulation, it's widely applied in environmental sciences. And what is the purpose? The purpose, rather than building on the knowledge of the physics, as I said, the purpose is to build on past observations. So you look at patterns in the past and you create future predictions which are different with respect to what you observed, but with the same pattern. And by saying the same pattern, I mean with the same statistics. same average, same variability, etc. What is the advantage? As I mentioned before, the advantage is that for those part of the process that we don't understand, we resolve the problem by emulating what we observed. So let me give you an example. We mentioned long-term droughts has a critical risk for modern society. These long-term droughts are probably due to natural variability, and the literature is pointing out that climate models probably cannot reproduce this kind of risk in a comprehensive way. So what could be an alternative? An alternative is to look at the past, to look if in the past we observed I have seen the question on the chat, I reply later. To look in the past and to see if in the past we experienced long-term droughts. If the answer is yes, now let's generate a scenario that for the future reproduces the same chance of having a long-term drought. And I could give you several examples of what I mean, but for instance, let me show you a web page. So let me open a web page, and I think I need, let's go here, not here, sorry. Give me 1 second, here I am. So let me look at a web page and search on Google. Let's search for drought Australia. Sorry, drought Australia. Now, if you look in Google, you see that there is an entry, drought in Australia. So what is this? This is an history of the droughts in Australia. It dates back to the 19th century. So why was this history compiled? You see, droughts in the 19th century. And it's 1803, 1809. Why is this history again compiled? The reason is to decipher natural variability, to produce simulations of the likelihood of droughts in the future. And this was particularly motivated by the occurrence in at the beginning of the 2000s of the so-called millennium drought, which was a drought that lasted 10 years and then ended in 2010. So in order to better understand the likelihood that a similar event may occur again in Australia, they explored the past. This is an example. Now let me look at the chart and let me go back to what is the difference between mathematical models and stochastic simulation. Let me say, as at the beginning, you may remember, I said any prediction in climate science is obtained through a mathematical model. Mathematical model is a set of equations of mathematical relationships. Okay, look at the nature of these relationships. Do they come from physics? Then this is a physically based model. If the equation come from statistics, then it's a stochastic model, still a mathematical model. So mathematical model is the main category, and you have two subcategories, physically based and statistical. And statistical, I mean stochastic. As I said, let's treat them as synonyms. Now, what is the main limitation of this approach? Statistics. The limitation is that if there is climate change, you cannot take it into account by looking at the past, because in the past there was no climate change. At least there was not the global warming. So on the one hand, you have the problem that GCMs may fail in accounting for natural variability. On the other hand, you have the problem that statistical models, stochastic simulation may fail sorry, in accounting for climate change. So you understand that probably the ideal solution, and this is what I'm trying to propose in the context of engineering, in the context of scientific journals, you may realize that the ideal solution probably is to make a mix, to blend the models, to make, for instance, a statistical model, to develop a statistical model that uses the climate model to take climate change into account. Or conversely, you may build a climate model that takes natural variability into account by profiting from statistics. There are, in the first category that I mentioned, several examples of applications already. So stochastic simulation by using climate models, it's already a category of models that have been tried. The second category, climate models profiting from statistics, it's more at an earlier stage. Some people, what they did was to generate with a climate model and then to introduce the so-called bias correction. What is bias correction? It's a way to incorporate a statistical approach into a climate model. And in practice, you apply a climate model and then the climate model fails in reproducing some behaviors, and then you correct the output. You fix the problem. This is bias correction. Bias correction is fixing a problem. I am insisting on the concept of bias correction because if you look into the science of climate change, you will see that bias correction is mentioned in several instances. And I think you need to understand what it means. Again, it's a correction, bias correction. It means that there is a bias in the climate model and we correct it. It's a different story than blending two models. If you make a correction, if you make a kind of post-processing, it's not an integrated model. So for this reason, I say that this category of physically based plus statistic models are at an earlier stage. I want to give you an example, and let me refer to the web page in my website, which is, let me see, I think it is here, climate models. Here, I put a link on a paper that I read 2 days ago, was just published. And I think it was a good example. So let me find it. It's Kiem et al. Here it is. Let's look on let's click on the link of this paper where they indeed apply stochastic generation of future hydroclimate using temperature as a climate change covariate. I think this is a nice example. It is a very simple approach. I mean, it's a smart and simple idea. What they do, look here, and this is a top category journal in the field of hydrology, environmental modeling. So the impact factor is okay. I mean, this is a reliable contribution. It's peer reviewed, of course. And let's focus here. Just 1 second. In this study, we develop an approach for stochastically generating future seasonal, monthly to annual, hydroclimatic conditions at multiple sites for water supply security assessment that capitalizes on an Australia-wide relationship between annual average, daily maximum temperature, and annual rain. What they do, they perform a statistical simulation that doesn't account for climate change. And then they use the output from climate models to predict the future temperature, and then integrate this prediction into their simulation by using a temperature rainfall relationship. And let's read here. This approach is practical, as it avoids the extra time and additional uncertainty introduced by downscaling and bias correction of climate model produced rainfall information, and takes advantage of the fact that climate model projections for temperature change are more realistic than climate models projection for rainfall. It is a very smart idea. In this case, they use the climate model to predict temperature, not rainfall, because they don't want to use the climate model for predicting the rainfall because it's uncertain. And then they use a temperature rainfall relationship that incorporate into their statistical approach. This is a nice example, and I think we need to move forward with this. I told you that, in my opinion, this is a very clever idea, which I'm trying to promote. When I saw this paper, I thought that there are other papers, by the way, but I thought that it's very good. And I would say that it is a bit trivial to take into account only the temperature prediction of climate models. I think a more extensive relationship, a more comprehensive relationship between the two models should be included. But I think it is a nice example and a good step forward. Okay, so conclusions of this discussion that we had today. Climate models are continuously evolving. The purpose of modeling is essential for model selection. Models for testing hypotheses are different, as I said, with respect to models that are applied to support technical design. I also see there is a question on the chat, so I will answer later on. Climate models may underestimate natural climate variability. And when dealing with poorly known natural system, one has to be aware of uncertainty. It should be dealt with by profiting from all the available information and all available models. So let me look at the chat first of all before I conclude this lecture, and then I pass to the next one for the last half an hour. There is a question from Mattia on the chat. What about the cultural variabilities from an anthropological point of view? Are these considered in these models? The answer is no. These variabilities are considered in the computation of the emission scenarios. And, you know, there are a lot of things that are neglected by climate models, and one of these things is the relationship with humans. Humans are not included in climate models. The only way they take into account humans and society is through the inputs, through the emissions. There are, of course, many people who say that a good model, a good environmental model, should nowadays include humans in a more explicit way. The integration should be more comprehensive, not just through the inputs. But, you know, this is challenging. We have to understand that these models cannot be, the more you increase the complexity, as I said, the more you increase uncertainty. So I think it is fine if some parts are neglected, but I would say it is fine as long as we are able to decipher uncertainty. And actually, I think the main problem for climate models from a technical point of view is precisely the fact that we still have a limited capability to estimate uncertainty. And this is why I say, look, if you bear a responsibility, if you take the responsibility for suggesting or designing actions, it's really important that you are aware of all the possible solutions. We are aware of all the facets, all the interpretation of the current debates, the current open issues. So it's important, because no matter if an interpretation is a minority rather than the majority, you have to be aware of everything is available, what are the uncertainty, and etc. Of course, you have to rely on good information. So the problem with climate is that information is very wide, and there are some reliable sources and some sources that are less reliable. So of course, we have also to be able to make a selection. And this is particularly difficult with climate, but not only with climate, also with water, also with everything is relevant to global challenges. Okay, if you don't have any other question, I would like to move to the next one. And in any case, if you have any question about these models, just feel free to ask me. Probably it's better if you write in the chat of Teams so that everyone reads it. And one more thing I wanted to tell you, I think you may get increasingly concerned about the questions that I may ask at the exam. I aim to make available, I would say within a couple of weeks from now, a trial quiz that I may propose at the exam, of course, by assuming that so far only a small part of the program is completed. So I think the best way to make you aware of what are the questions that might be asked is to propose to you a test that you may repeat several times, etc. So I aim to do this, as I said, within a couple of weeks, because I need to wait a little bit, because now I wouldn't have enough questions to make a representative picture to you. I need the next couple of teachers to speak, and then I can elaborate the questions on the basis of what they give to you. Okay, and let me look at the chat. It's everything seems to be okay. One thing I wanted to tell you, let me go back to the page of climate models. Here in this page, there is a part that I didn't cover, which is technical application and solution for climate change mitigation and adaptation. Please forget it for now, okay? Because this is an extra that I want to make later on, if in my last lecture, if I will have the time. Be patient with me, because you know, I prepared a lot of material, but I still need to see what is feasible. And also the same applies to the exercises. I need to see what is feasible. I already have a couple of exercises prepared, but I prefer to wait for the next my lecture, which unfortunately may be the last one, to make something together related to exercises and also related to solutions, more specific solutions. Okay, now, so forget about this. Section 7 of climate change and of this lecture, which is called climate models, sorry. Now, let me go back to, oops, here it is, to the next one, climate change and water cycle. Not found. Okay, so the link is wrong. Let me go to it. You can find it directly from my website. I will fix the link now, but it's here, lecture climate change and water cycle. If you click on the left column, but I will fix the link just in a few seconds. I am just curious. So this is the correct link. I think it was a cut and paste error. So this lecture is, let me introduce it. And yeah, thank you, Giacomo, for the correct link. This lecture is quite extended, and also it incorporates an introduction, which you need to skip. So section 1, because we already discussed it. So, and I would say, okay, I think you can start from section 2. this section is, and also there are other subsections that you will see that may discuss things that we already discussed, like climate models. They are briefly mentioned here, so feel free to skip what we already discussed. What is the purpose of this lecture? Is to give you a more detailed treatment with examples of natural variability of climate. This is section 2, by focusing on several variables, and human influence on climate. This is again a more detailed treatment discussion. Also, there is a discussion on recent changes, section 4, in hydrometeorological variables like precipitation, etc. And then you have later on again, and here there is a discussion on sea level rise, etc. And then there is a discussion on the impact of climate change on flood and droughts. Now, Veronica Rossi is going to deliver 3 hours lecture next Monday on the history of climate. I believe she will focus on glaciations, and I don't think she will focus on specifically on single variables like the variables of the water cycle, for instance, floods and droughts, etc. So I really believe that reading this lecture, which is a long-standing one because it was prepared a couple of years ago, you see the number of accesses is more than 17,000. So I really believe that this lecture is a good integration of what Veronica will tell you. So what is my proposal? Because now we have 20 minutes to go. My proposal is that you make the effort to read this lecture. And I think that at the beginning, besides the introduction that you can skip, natural variability, I think Veronica is going to talk about it. Here you see a picture of glaciations. And here you see a picture of long-term changes of temperature, long-term changes of carbon dioxide, dust concentration, etc. I think Veronica is going to speak about this. So I will not focus today in these 20 minutes on this first part, okay? And I would like today to discuss with you and neither the human influence, because I think that probably Veronica and Antonio Navarra will discuss this. I want to focus today in these 15-20 minutes on recent changes in other meteorological variables, because I think that Veronica will not discuss this. So the moral of the story is now I am talking about 15 minutes on this, and maybe after listening to Veronica, I suggest that you take a read to this full lecture. You will see that some sections are already dealt with in the previous lectures, including Veronica's, which is fine, you can skip it. But I think that this is, overall, it's a very nice integration. And it is one of the things that I will, together with the other teachers, ask you to study, at least in part, independently. There is just one thing that I want to focus your attention on the first part, which I think Veronica will discuss. It is this picture. This picture is a reconstruction of the past temperatures, and you need the axis, the scale of the horizontal axis is thousands of years ago. So it goes back 400,000. It's not very far in the past. Veronica will talk with you about millions of years. What I want to discuss in this figure is the high correlation, the high correspondence between the concentration of carbon dioxide and temperature. This is due precisely to the fact that the oceans, for increasing temperature, release a lot of CO2, which means that, you know, there is a direct connection between temperature and CO2 release from the oceans. Anyway, you can see that if you go back in the past for only 400,000 years, the current concentration of carbon dioxide and the current level of temperature is quite high. If you go much further in the past, then you would find the concentration of carbon dioxide that were higher than now. But in the, let's call it in the recent past, where by recent I mean 400,000, we have now high temperature and high carbon dioxide concentration. Okay, now let's focus on recent changes. Precipitation. So is precipitation changed in the recent past? Where with the recent past, I mean the past 30 years. I mean the period, the global warming period. This is an open question for most of it, meaning that if you look at the overall global precipitation, it's more or less unchanged. If you look at the local level, you may see some changes depending on the region. If you look over Europe and you look at the annual precipitation, so the depth of rainfall that we observe each year. So let's suppose that you put a pot out of your home, out of your door, and you leave it there for 1 year and you collect all the rainfall and you assume that you have no evaporation. At the end of the year, you get an estimate of the annual rainfall, which is at the global level something less than 1 meter. And the same amount of rain you would find in the north of Italy, more or less. It's about, in Bologna, is about 800 millimeters per year. This amount of rainfall in Europe is not changed much. In some regions of the world, we observed a decrease to which corresponds an increase somewhere else, but still the changes are not very relevant. So it looks like that for what matters, water resources availability, there are not relevant changes. If you look at the rainfall in a short time step, like for instance, the very heavy rainfall that lasts for 5 minutes, you know that there is a lot of discussion about this, and it's related to the fact that some people think that heavy rainfall have increased in magnitude. The answer is undefined, meaning that we still have a limited data coverage. I think an interesting example, by the way, is a contribution that I had the opportunity to lead, which is based on the analysis of a global database. You see in this picture of the world, the distribution of the data set. Where you see the colors, it means that we have coverage. And this is a database of daily rainfall, which is about 50 years long. And what you see is that, what we could see is that, first of all, if you look at the number of extreme rainfalls, there is an increase. So we see that overall, it looks like the frequency of extreme rainfall is increased about 20%. It means that if an event occurred in the past once per year with such high intensity, now is occurring, or let me say, if an event was occurring 5 times in 5 years, now we observe 6 events in 5 years. So there has been some increase in the frequency. Actually, the magnitude, so the intensity of the event, is not increased much. This is what daily rainfall tells us. This is a paper that had a great visibility because it's based on the analysis of some 70,000 records, which is a lot. For shorter durations, we don't have such coverage. And why this is important? Because there is a huge question mark. Are floods increased under global warming or not? If you look at the media, it seems that they are increased. If you look at the amount of the damages induced by floods, they increased a lot. But the damages are due to a mix of drivers. One driver is climate change, of course. An increase on the damages may be induced by climate change, but an increase of the damages can also be due to increase of exposure. It means that the value of the exposed land is increased. Actually, it looks like the increase of the exposure is dominating with respect to climate change. This is a big question mark, which we need to resolve because we need to solve a problem. The problem is increasing damage and the increased number of deaths due to floods. So the solution is different depending on the cause. We need to understand the cause. And I mean, in this case, it's we need to understand from a technical point of view. So the question on whether the changes rainfall is changed is really very relevant in this respect. I am skipping these figures which report the same analysis, not at the global level, but at the detail of each single continent. I skip it, I leave it to you to read. Now, sea level. Did we experience recent changes in sea level? I start from this figure, which shows a progress of sea level rise starting from several thousands of years ago. Of course, we are moving out of from a glaciation, and therefore the sea level is increasing. But what happened in the recent past? So let's look at a recent picture. I go down. And this is the progress in sea level change. I think I already shown this picture to you. I have already shown this picture to you. This is the sea level change in the past 120 years, I would say from 1880 to 2000. And you see that there is indeed a steady